Hey guys, we're going to recap everything we've done up to Module 3, Sections 1, 2, 3, 4, and 5 with this simple set of notes on how to graph any polynomial. So I'm going to go through our steps for graphing any polynomial, and then I'm going to do the very first practice problem on task 3.6. Now, like I said, this is going to bring together everything we know about polynomials, everything we've learned up to this point. So when I look at graphing a polynomial, this is the order I go in. These are the steps that I follow. First thing I do is I want to look at the degree. When I'm looking at the degree, I'm trying to determine what the overall shape of the graph is going to look like. If we remember, x to the first looks like this, x squared looks like this, x cubed is going to have this kind of curvature to it. We call it an inflection. X to the fourth is going to create that similar curvature, but this time it's going to be a W shape. And x to the fifth is going to keep the pattern going. And when we say degree, we're actually getting the end behavior from this. If you notice, our odd functions go to opposite ends. The negative side goes down to negative infinity. The positive side goes off to positive infinity. And when I think about an odd function, I know that one side's always going to negative infinity, one side is always going to positive infinity. Well, then if I look at my even functions, I should see that they both go in the same direction. Both sides here go to positive infinity on that x squared. Both sides here go to positive infinity on that x to the fourth. So the first thing I do is look at the degree and determine what direction it's going. But I can't just look at the degree, I also need to look at the leading coefficient. So when we find that highest power, that highest degree, we want to look at the coefficient. And that could turn our graph upside down. For example, we've established that our regular x squared function, the end behavior goes up to positive infinity on both sides. But if I had, say, a negative x squared function, that would turn it upside down and it would go to negative infinity on both sides. Same with any odd function. If I had my positive x cubed, it would create that kind of curved shape where it goes to negative infinity on one side, off to positive infinity on the other side. But if I had a negative cubic function, it flips it upside down. So now we start off going to positive infinity and end up going to negative infinity. So my very first step in graphing any polynomial is to assess what the degree is, so I know what general shape to create, and the leading coefficient, so I know whether that end behavior is going to be positive or negative. So I've got the degree, I've got the leading coefficient. Now it's time to plot my x-intercepts. And this is the most level of detail that we need on x-intercepts. We need to know what they are. X-intercepts, whoops. Let's fill that in, intercepts. There we go. X-intercepts are anywhere that our function equals 0. So what we're going to do is we're going to set the whole function f of x equals to 0. That usually means we're going to have to factor and set individual factors equal to 0. But once we set those individual factors equal to 0, we should have some ordered pairs for where we want to plot our x-intercepts. But don't forget, we also need to define their multiplicity. So if that term, x plus or minus a number, was raised to the first power, we call that a single root, and it's going to pass through the x-axis at that point. If that factor, we'll say x plus or minus another number, was squared or raised to the second power, it's going to behave more like a quadratic, and it's going to bounce off or create this kind of parabolic shape. And lastly, if that x plus or minus a number factor was cubed, that's when it's going to behave more like a cubic function, and it's going to have an inflection right at that point. Now, our inflection is our math word for this kind of curve that happens at the x-axis, where it kind of slows down and flattens out at the x-axis, but then keeps going. So we have our general shape from our degree and our leading coefficient. We now have our x-intercepts by factoring and segging equal to 0. We have pretty much everything we need. Now let's give it some detail. And that detail is to plug in some points between the x-intercepts, including the y-intercept. So when I say plug in some points, you want to plug in maybe 1 or 2. Plug in maybe 1 or 2 points to the original equation. And don't worry if these points go way off the graph. The whole idea is just to double check that you've drawn your sketch correctly, that it's positive where it should be positive or negative where it should be negative. Now, the one point that I should see really clearly is that y-intercept. And there are 2 ways we can find the y-intercept. First, we can plug in 0 for x, which is also just called f of 0. Or we can just look at the constant. If our function has a constant on the end, that is going to be our x-intercept. Or look at the constant. Okay, so we found the general shape of our function by looking at the degree and the leading coefficient. Then we plotted specific points, our x-intercepts, making sure to graph them with that right shape based upon whether it's to the first power, to the second power, or the third power. And lastly, we've given our graph a little bit more detail by checking some points in between the x-intercepts and plotting that y-intercept. All we have left to do now is connect the dots and graph. So let's try an example. This is number 1 on task 3.6. I'm going to run through these steps just like I did before. So, first step, look at the degree and leading coefficient. We have to think about the degree here. We have x times another x. So our total degree is going to be x cubed. And we did have a negative in the front, so it's actually going to be negative x cubed. So we bring this all together and we have negative x cubed. So that means, just to give ourselves a general shape, x cubed looks like this. But we are going to be flipping that upside down, and our general shape should look like this. So what I'm going to do is I'm going to draw myself an arrow right here to remind myself it's going to start from that direction, and then an arrow down here to remind myself it's going to end in that direction. I want to make sure that it starts up here and ends down here. Okay, so that's step 1. Look at the degree and leading coefficient. And we can actually fill in that end behavior now. The negative side goes off to positive infinity. That's right here. And the positive side goes off to negative infinity. That's down there. So step 2 is find roots. Find the roots with their multiplicity. Now this is already given to us in factored form. 1, 2, 3 separate factors. We're going to set each one of these equal to 0 to find our roots. So the first one is just x equals 0. The second one, x minus 2 equals 0. Add 2 to both sides. X equals 2. The next one, x minus 4 equals 0. Add 4 to both sides. X equals 4. So we're going to plot 0, 0, 2, 0, and 4, 0. And a quick scan of these shows they're all just to the first power. So they all should pass right through like linear equations or straight lines. So here I'm going to graph 0. Here I'm going to graph 2. Here I'm going to graph 4. And I do know they're all going to pass straight through like straight lines. None of them are going to bounce off, making that quadratic shape. None of them are going to kind of inflect like that cubic shape. So last step on this one is to fill in some points in between just to give it a little bit of detail. We already have our y-intercept. That is right there at 0, 0. So we don't need to worry about that. Instead, let's maybe plug in 1 to see if it goes up or down, and 3 to see if it goes up or down. Now, ideally, I think I know which direction it's supposed to go in. I think since it's supposed to start up, it's going to go up and turn around like that. But we're plugging those points in to kind of confirm that we have the right idea. We're checking a few points to make sure we've done this correctly. So I'm going to make a little table and I'm going to plug into the equation above. I'm going to plug in just 1 and 3. Make this a little bit smaller so we can see it. So I'm going to start by plugging in 1. That's f of 1 is negative 1, 1 minus 2, 1 minus 4, or negative 1 times negative 1 times negative 3, which is just negative 3. So that point actually gets plotted right there. Hey, we were on the right track. We thought it would be underneath the x-axis or it would be negative at that point, and it was. Now let's try 3. So this would be f of 3, which is negative 3, 3 minus 2, 3 minus 4, or negative 3 times 1 times negative 1, which in this case is just positive 3. So that point fills in right there. And hey, we were on the right track there too. We thought it was going to be positive above the x-axis, and it was. So there we go. We have our graph. I'm going to go ahead and fill it in blue, a little bit heavier, so we know that this is the correct graph. We start from positive infinity, pass through 0, turn around, pass through 2, turn around, and go off to negative infinity. That right there is a sketch, or this one is actually more of a precise graph because we have some points in between. But that is a sketch of the function that was given, f of x.